Working. You guys can see my screen, right?
Yeah.
Okay, good. Usually there's like a border around it when it we're talking about points moving on a moving or on a rotating frame of reference, right? So this point P, say, is on this slab, and this slab is rotating with, large omega. So omega, the omega here that you see here is basically the angular velocity of the frame of reference. So that's why they're using the big omega. So I just wanted to clarify that. Let's see. Oh, and VP, right, is a combination of VP prime, which is this omega cross R, right? So this is the component that's due to the object rotating, right? And then you have a velocity P with respect to the frame of reference OXY, like the small x, little x and y. Oh yeah, that's right. This is where it got complicated. So it's moving with respect to that coordinate system, right? So that's this term V of P, right? The velocity of P is a function of both of those vectors. VP with respect to the frame of reference is a little more complicated to get, but this is the direction it's moving. So this is an equation that we'll be using for velocity. And then when we get to the acceleration component, all you're doing again is recognizing normal and tangential components, but now you're also putting that into rotating frame of reference. So let's see, we've got VP, we got an equation for VP. You can take the derivative of this, right? And you get the acceleration. So basically substituting back in, right? Omega cross R, you got the dot. This is basically taking the derivative of the whole thing to get the acceleration of point P. And some of these terms are not, or yeah, some of these terms, depending on your situation, will cancel out, right? Like for constant angular rotation of your frame of reference, your object, your rotating object, right? This is going to go away, the omega dot term. Also, if you're not accelerating, right, that's going to go away. This is the conceptual point P prime, right? We talked about that. That's the one that's sort of on the slab, moving at that instant with P. And you wind up with terms for the acceleration of the particle. So you're starting from this equation basically, and then you're just basically canceling out what you don't need as you go along. But what they're showing here is that AP prime, right? These terms right here are AP prime. This term over here is AP with respect to the frame of reference, and then you're left with this Coriolis acceleration, which is this 2 omega crossed with R dot. Now R dot is actually V, right? V of P with respect to the frame of reference. So that's where you get this substitution going on. So, I mean, you can write out the general form and then you can just substitute in what you need. All right, let's look at this problem here. This is a collar. Collar slides along at a constant relative velocity, U. So notice the constant velocity U along rod OB. And the rod's rotating at a constant angular velocity omega, right? So the rod now is like our monolith. It's our frame of, or our moving frame of reference. And right now, this is at position P, right? The collar A. So what do we got? We've got an acceleration. I don't know why it's labeled with an A. That should be a normal. R omega squared towards the center, right? Normal. And you've got, oh, okay, yeah. They they labeled the accelerations from the, and you got a Coriolis acceleration. So let's see how we get these things. The absolute acceleration is going to be A of P, right, is A of A plus A of P with respect to the frame of reference moving plus the Coriolis acceleration. So A of A, right, is this omega dot cross R plus omega cross R. Now, this term here, right, we've got constant angular velocity. So this term is 0. And we're left with basically R times omega squared. That's where the acceleration of A comes from, right? This acceleration here. That's where this, I forgot this is a diagram, just pops up as one with the answers in it. So we have to just sort of go through. With respect to the rotating frame of reference, right? The previous slide showed this term here, A of P with respect to the rotating frame of reference is the second derivative of position, right? Which is acceleration of, now we don't have, we have this thing moving at a constant velocity, right? U. So this is the first derivative of this, right? With respect to OXY. Remember, little x, little y is the rotating frame, right? That is, the velocity is constant. So then the first derivative of velocity is acceleration is 0. So that term goes away. And then we're left with the Coriolis acceleration, which is the 2 omega cross VP of F. Now, VP of F we have, right? That's U. So that's just, this turns out to be 2 omega U. And that's where this Coriolis acceleration comes from. And you can see here, right? These are radial and tangential vectors, right? Same as we would normally get, except this is derived using the fact that there's a frame of reference moving, right? You don't just have the collar moving this way, you have the entire rod moving with an angular velocity omega. Let's see. If you take this, let's take this collar and let's take 2 positions, right? This position here, a starting position, and then a second position here. So there's some increment of time that carries it through this delta theta, right? And you can see the velocities. VA is R omega, and U is here. Here we've got U prime, and here we've got VA prime is R plus delta R omega, right? So we're moving this incremental distance, sorry, this way, delta R, and we're also moving an incremental theta, right? And you can write expressions for time or at different times what those velocities are. Basically, we can write a vector formula, or we can graphically sketch out the vectors, right? We can look at R, this R prime, R to R prime is this difference between U and U prime, right? And then T to T prime and T prime to, sorry, T to T double prime, right, is one vector, and then T double prime to T prime is another vector. So that gives us our overall change in this VA, right, VA to VA prime. That's the difference between these 2 vectors. So we can take VA and VA prime and break it down into, with respect to that frame of reference, right, a vertical and a horizontal vector. And notice this T double prime, right? Change in direction of the velocity at point A on the rod. So you can now take the limit as these things, as time gets small, right? So this thing goes to 0. So theta goes to 0, but also delta T is going to 0, right? You wind up with a limit equation, which brings us to the acceleration of A is R omega squared, which is what we got in the last analysis, right? And this is just the formula we used before, right? So we get the same thing. This is just showing physically what's going on. Yeah, and you can do the similar thing for R r dot or r prime and t double prime t prime, and you can also take those, add them together, right? Take the limit as you approach 0, and you get u omega plus omega u equals 2 omega u, right? Which is what we got up, well, previously on the previous slide for the Coriolis acceleration. All right, let's look at a problem here. We have two disks. This is called a Geneva mechanism. This is kind of a neat mechanism. Basically, one disk rotates. You've got a pin that fits into a slot, rotates this other disk by a quarter turn, right, and then comes out. So depending on the number of slots you have, you can take constant rotational motion, right, and you can turn that into incremental motion. And yeah, it's a Geneva mechanism. It has you may be familiar, if you're familiar with, like, old clocks. This mechanism is used in that. Let's see. Okay, so it has a disk D here is rotating with counterclockwise angular velocity. Omega D is 10 radians per second. So this way, which makes sense, right? So this is going, well, it could go the other way too. This is going into the slot at this instant here, right? At the instant when phi is, why is there an angle difference? 150 degrees. The diagram is labeled 135. We're going to work with 150. Determine the angular velocity of disk S. So what's the angular velocity of disk S? And the velocity of the pin P relative to disk S. So we're gonna figure that out. We're gonna write the general velocity P, right? As P equals V of P prime plus V of P with respect to S, right? Disk S, the rotating frame of reference. We can get V of P, right? We can get it from the radius and angular velocity of disk D. So we're going to do that. And then velocity of V of P prime, right? P is perpendicular to the radius OP, right? OP right now. So we can use that relationship to get the direction. And it's also V of PS is of P with respect to S is parallel to the slot, right? So it's moving, at that instant, it's moving into the slot in this direction. Now, obviously, it's going to change at time greater than wherever we are. So we're going to use it. We're going to draw out a vector triangle, and we'll solve that. Oh, that's funny. My camera froze. Okay. Let me just write down the VP equals VP prime plus V of P with respect to the, now instead of that fancy S, I'm going to use, or the fancy F, I'm going to use S for our frame of reference, disk S, right? Because we're looking for angular velocity disk S and the velocity of pin P relative to disk S. It just beeped. Is my phone again? What the hell? All right, my phone's got a mind of its own, apparently. Let me write it over here. V of P oh my God, I know my phone is in airplane mode. Stop talking to me. R, what was I doing here? Oh yeah, VP is R omega D. Oh, R, that's R. Oh, both R's are the same. Let me draw the omega on here. All right, so the velocity of P, right, is without the frame of reference of S, is just by itself the radius times omega D. which is equal to 50 millimeters times 10 radians per second. Oh, why did I square that? So we've got 50 millimeters per second. So that's the velocity of P all by itself, right? I'm going to draw out a portion of this disk here. So bear with me. Let's see. We'll draw the slot. We got the other disk kind of going like this. And we've got the pin. This is D. This is S. Over here we have from the center of S, right? We're going to have right down the line. This is R. This pin, right, has its own, I guess, this disk D is not very well done, but this is an R. This is a radius R. It's a sketch. What do you expect? Radius R. This pin, this pin has its own radius to the center of D, right? And so let's call this point B, right, from up here. And this is point O over here. Then we got this angle in here. This is, let's see, this is given as 150 degrees. I know it says 135, but we're working with 150. I don't know how the problem got switched, if that was the original textbook problem. So this is 30 degrees here. This length, L, so right now I'm just trying to get some information. So in the case of force laws, this occurs when the distance between centers of the disk is L is square root of 2R. So this is square root of 2R, right? This is what this looks like geometrically. So we're at little r, that's big R. Yeah, L. You know what? Oh, they did define L here. Okay. So now what we can do is we can actually figure out R here. We don't know, are we given the radius? Well, let's write this out. We can use law of cosines, right? Because we don't know for sure what this is, but we know this R and this L, right? R squared plus L squared minus 2RL cosine 30. We don't know that this is at radius R, right? All we're told is that the information that we're given is with this distance and this distance, right? The pin enters and leaves. This occurs when the distance between the center is L over. So this is that instant right here. We don't know this is a 90-degree angle, even though I'm sure you're tempted to want to say this is a 90-degree angle. So I'm using the law of cosines to figure out, I know this distance, I know this distance, I know this angle. So you wind up with, let's see, once you plug in the numbers, oh, this is supposed to be a big R. So if you plug in the numbers for R, and L, you wind up with R squared equals 0.5505 of R squared. Because L is also a function of R, so you wind up with an R squared here and R squared here. These can all be substituted in, right? Just make a note here. L equals square root of 2R. Right, we can substitute that in. So if R is 50, you wind up with R, little r, equals 37.1 millimeters. This is just geometry here. Has nothing to do any at all with anything that we've done so far. We still don't know beta. We can get beta from law of sines. Get beta. Let me just draw an arrow up here. From law of sines. Right, sine beta over the opposite 50 is equal to, we have sine 30 over the known radius r. What's r? R is 37.1. So from here we get beta is equal to 42.4 degrees. Now, I want to draw out some vectors here. We have VP with respect to S is at that instant moving towards the origin, right? So that's VP with respect to S. That's going to be at the 42.4 degrees. So let me draw out an axis here. This is V of P with respect to S. All right, and this is 42.4 degrees. We also have V of P, which is moving, again, these diagrams, this diagram here is a little, it makes it look like it's moving in a 90-degree angle, but V of P is moving along like this. Oops. And then we have a connecting V of P prime. Let me label a few angles in here. And leave room for my axis here. This 30 degrees, right, gives us this 30 degrees here with respect to the vertical. Just because of the velocity that it's moving. Let's see, V of P, where's the, V of P is basically 50 omega, right? So it's the tangential velocity to this, right? So this has got a velocity 90 degrees. This is at 30 degrees. So an angle vertical with that is going to be 30 degrees right here. I know it doesn't look like 30 degrees, but that's what it is. And then gamma is going to be 17.6 degrees because it's 90 minus 30 minus 42.4. This is a 90-degree triangle right here. This is definitely 90 degrees. Oops. So VP prime is at 90 degrees of VP, V of P with respect to S, right? This is just the vector notation or the vector form of this equation. So we know the weird part about this is we know this part, we know VP, right? We don't know these other, so VP is the hypotenuse of this vector triangle. And we know it's the sum of VP prime plus VP with respect to S, right? We don't know all that information. So we gotta draw out a vector triangle. So VP, oh, it's pointed this way. So this is kind of weird to try to visualize on a rotating frame of reference. This is why I think people have trouble with these problems because they're not intuitive. See, oh yeah, this is moving. This P and this P in tangent, right? Disk S is rotating this way. The instantaneous point, that's what the VP prime is, right? Is moving along this direction somehow, right? Because this is moving and this is moving. So it's just, it's moving sort of in line with it at that instant. It's instantaneous. So it's very, that makes it harder for people to wrap their heads around. So from geometry, we can see VP prime is just VP sine of gamma. This gamma here. So 500. Oh, this is a 500. I don't know why. 50 millimeters times 10 radians per second. That's 500 millimeters per second. 500 sine 17.6 degrees. VP prime is 151.2 millimeters per second at an angle of, and you can notice here, right? We can use, well, this is 42.4. We can figure out that this is 42.4 from the top, this top horizontal here, because this is at 90 degrees, right? So it's 42.4 degrees. Let's see, it's actually, hold on a second. Oh no, it's this, right? Opposite interiors. This. This goes to this right here, 42.4 degrees on the inside. Draw that like this. Yeah, you have to sort of go over here. So let's see, this 30, 90, 60. Then you've got this this portion in here that's got to be split up. So you figure this out, and you get the 42.4. You got the 90 degrees, you got the 90 off of that. That's where you get the 42.4 from. All right, so VP prime is perpendicular to OP. Right, OP is this angle, or this radial, this radius here. VP is perpendicular to that. Sorry, VP prime is perpendicular to that. VP prime. We know VP prime is R times omega S, right? So omega S is the angular velocity of disk S, right? So we can find that by dividing VP prime by R. So here we get omega S is 151.2 millimeters per second divided by, little r, 37.1 millimeters. This is 4.08 radians per second. And this is clockwise, right? And you can kind of see that in the problem, right? This disk is rotating this way as this rotates and pushes it down, right? VP with respect to S, this term right here is going to be VP cosine gamma. So just like this was VP sine gamma, we're going to get, let's see, 500 cosine 17.6. Here we get 476.6 millimeters per second, and an angle of, this angle is 42.4 degrees that way. Now, you can also write this in vector notation, right? This is VP. So 476.6, because of the angle it's at, right? This is a decimal. 476.6, we've got a negative cosine, 42.4 I. And then we also have a negative sine. So this becomes VP with respect to S, negative 352I minus 321J. And this is millimeters per second. So we found the angular velocity of disk S, but you know what? I didn't actually circle here. That's the angular velocity of disk S and the velocity of the pin relative to disk S. That's, I mean, this doesn't make maybe as much intuitive sense as this does. 476.6 millimeters per second at that 42.4 degree angle. Now notice the velocity of the pin is 500 millimeters per second, right? And that's directed down like this, basically tangential. Again, the sketches are not the best. This is sort of an idealized scenario as well, because this looks like the pin is just entering the slot, but in reality, it's actually moving with the slot. You don't know, like that distance R we found is the distance, you know, the pin is in contact with the slot. So maybe I need to draw this a little differently next time, but the pin is touching the disc, right? It's moving it. And that's why at that instant, right, 150 degrees, oh, I think that's probably where the 135 comes from. That's where it starts entering the slot. Yeah, that's where it comes from. All right, so this is example 8. I'm going to start example 9 because it's basically right off of this one. It's the same mechanism, except now we're dealing with accelerations. And we're going to use this information that we got here as part of the accelerations or the acceleration problem. So now we've got the Geneva mechanism again of the last problem. Disk D rotates with counterclockwise angular velocity of 10 radians per second. Let's put this omega in here again. And again, at the instant when phi is 150, right? So phi is now greater. So that's all they're trying to demonstrate. I'd forgotten this problem is set up weird. At 150 degrees, right? Now you've gone from 130 to 150. Determine the angular acceleration of disk S. So not only is this pin spinning disk S, right? It's taking disk S from basically rest to some through some velocity profile, right? And it's accelerating it. So disk S is going to have an acceleration. So let's look at the acceleration of point P is now going to be AP prime plus AP with respect to S plus the Coriolis acceleration. Got another term in there. From 15.9, right, or 15.9, yeah, 15.19. This is the last problem we did, 15.19. Omega S is equal to 4.08 radians per second clockwise, right? And V of P with respect to S is equal to 477 millimeters per second. And I rounded from before, right? Before I had 476.6, but obviously I can't deal with decimal points, so I need to round here. And that was at 42.4 degrees from the horizontal, well, the negative horizontal. Omega D is constant, right? Let me write out A of P here. Since omega D is constant, omega D is constant, so you have no tangential acceleration, right? But you do have normal acceleration, right? Is towards B. B is the center point, right? So the acceleration is towards B. A of P is going to be fully normal acceleration. So it's going to be R omega D squared, right? The radius of 50. Again, this is the acceleration of P, right? Overall. So 50 times, what did I say? 10 radians per second squared. This is omega D here. So we got 5,000 millimeters per second squared. And this is at an angle of 30 degrees. Remember, that comes from the 150, the 180 minus the 150. Right, back here. This is our solid pin. So acceleration is towards the center of rotation of disk D. This is equal to A of P. Let me just put that in its own location here. So we've got that component. Let's look at the conceptual point, A of P prime. This is going to has A of P prime normal and A of P prime tangential components, right? So let's write this out. The normal component is R omega S squared, right? Remember, this is now with respect to, versus the S disk. So we've got little r, right, which is the distance on the S disk that it is. So it's, really the point's in here somewhere. Let's see, 942. We've got R omega squared S. We got 37.1 millimeters times the 4.08 squared. Is what? This is 617.6 millimeters per second squared, and that's at an angle again of 42.4 degrees, right? Pointed towards, again, the normal component is pointed towards that that center. I feel like I'm, oh yeah, that's right. All right. Let's do the tangent. Going in slightly different order than my notes, so I'm getting lost. This is just R times alpha, right? Alpha S. And this is what we're looking for. We're looking for the angular acceleration of S. So this is just 37.1 alpha S. And that's going to be angled, again, that's tangential to this one, or it's tangential to this point, right? This is the normal. The tangent's going to be off in this direction. It's going to be, again, a 42.4 degrees like this. Right, because you've got 90, this 90, 42.4. We don't know this variable yet, A of S. Let me draw another sketch over here. Well, no, we're working off the other sketch. I don't need to add that sketch. I should move over here and try to figure out. Do I have room? Draw a line. Let's see. So we've got AP prime, AP. Let's look next at the Coriolis acceleration. This is 2 omega crossed with R dot OXY. These are the little XYs, right? R dot OXY is just VPS, right? So A of C is equal to, we're going to just write this as 2 omega S VPS. In terms of the magnitude of this, right? This is going to equal 2 times 4.08 radians per second times the 477 up here millimeters per second. Oh, I don't need the. So the acceleration, the Coriolis acceleration is 3892 millimeters per second squared. And this is up in the 42.4 direction vertical like this. Well, off the vertical. That's the Coriolis acceleration, which again, because of the omega crossed with the r, right, the position vector r, well, r dot, right, it's the first derivative of the position vector, right, basically the velocity. Where's my, there it is. We're crossing it, right, so it becomes 90 degrees. So VPS is pointed like this, right? The Coriolis acceleration is like that. All right. What we got? Oh, yeah. Let's make a comment about acceleration of P with respect to S. Let's see. This is parallel to the slot. Right at that instant, it's parallel to the slot, right? The pin moves, pin P, moves in a straight line slot cut in disk S. Right. So if you're on the disk observing this, right, what do you see? You see this thing, this pin is coming straight toward, like say I'm sitting in the center here, right? The pin is moving along the edge of the slot, it's coming straight towards you, right? This is what you see. The acceleration of P in the frame of reference of S, right? If you're sitting on S observing it, it's coming towards you, right? Right along the straight line. This is what makes these problems so difficult to, again, intuit, right? You have to sort of think through, all right, what is going on here, right? So let's see. I'm just going to write a generic vector for this. Is going to be the whatever the magnitude of this is, right, at an angle of 42.4 degrees. So that's what it looks like parallel to the slot, right? Again, coming from this geometry, beta is 42.4 degrees. We'll make another note about AC. Oh, yeah, you know what? I meant to talk about the AC direction. Or make a note about it, direction. Right, the vector AC can be obtained by rotating VPS through 90 degrees in the sense of rotation of the moving frame. So remember I showed you up here, I said, okay, VP is, that's kind of what I was doing when I said, okay, VP is pointing, downward, right? I'm cross-producting this. That's kind of what you're doing, right? Physically, what you're doing is you're rotating it through the frame of reference, but mathematically, it's the cross product, right? So it's the cross product with the rotation, omega. So you've got this vector pointing this way, and you're rotating it this way, right? Oops. The frame of reference S is going clockwise. So that's why you're rotating at 90 degrees like that. It's basically the cross product. This is the physical manifestation of the cross product, this statement here. All right, it's 9:51. I'm gonna summarize here the equation, and then we'll come and start here next time, because we're not done yet, obviously. So we've got a normal component of acceleration P prime. This is for the conceptual point. And then we've got a tangential component. And we've got our P with respect to S, and then we've got a Coriolis acceleration. So write all those terms out when we get started here next time. Was there a question? All right. I'll stop here and we'll finish this on